Welcome to this OST2 lecture about platform configuration registers of a TPM 2.0. This topic was the most requested during TC1101, and we needed to gain some prior knowledge before reaching the PCR topic. So what is a PCR? Unique feature of the TPM. As the name suggests, any PCR is a memory register. That memory register can hold only a hash digest. The length of the digest depends on the algorithm. Typically, PCR registers support SHA-256, and if the TPM supports, for example, SHA-512, then the PCRs should be having banks also for that. SHA-1 is supported across any TPM 2.0. However, this is only for backward compatibility with existing systems, because SHA-1 is deprecated and insecure. What makes PCRs unique? The fact that the content of a PCR can be cleared only under very specific conditions. Usually these conditions are related to power on-off cycles and other limitations that we'll talk in a moment. Because of this, PCRs are difficult to tamper with. This is a quick overview of how platform configuration registers work. We already learned that PCRs are just memory registers that can hold a hash digest. What happens at system boot or TPM power on is that all of these PCRs get reset to either all zeros or all ones depending on their PCR number. And this is defined in the TCG spec, and we'll talk more about this later in this lecture. As a user of the system, there are exceptions for some PCRs when you can perform a reset. The difficulty of tampering with a PCR comes not only from the limitations on when to clear the content of a PCR, but also from the way we can write to the PCR. There's only one write operation available to us, and that's PCR extend. PCR extend is the operation of adding new information to the existing old one and concatenating the two hash digests. This means that the result, the third hash digest, will carry the information from the original old one and will be modified based on information from the new digest that we appended. Together with the inability to clear the PCR register, this means we can only add new information. And the order of adding information, adding hash digests, adds additional guarantees about the value of the PCR. The value of the PCR will be known to us only if we follow the same order with the same hash digest being extended. This makes the PCRs great tool for evaluating device health and system integrity and file integrity and so on and so on. PCR reset is the operation that we use to clear a PCR content. Most PCRs are reset only during power on-off cycles. Some PCRs are reset during power on and only in specific TPM locality. Very few PCRs can be reset at any time, and usually those are for debugging purposes, testing and development. It is not out of the question to use the PCRs that can be reset at any time for application purposes. However, we need to be aware of that other programs can extend information in that specific PCR. As mentioned, most of the PCRs can be reset under very strict rules. What is TPM locality? There are at least 5 locality levels from 0 to 4 that any TPM 2.0 has. The TCG does not limit the number of localities. However, it is the most common case to see from 0 to 4. The TCG specification allows a TPM to have up to 229 of these levels. So what is locality to the TPM? We can look at it as levels of access. Depending on the locality level, we are given certain capabilities and permissions. In relation to the PCR, this means that we have to be in a specific level of locality to be able to clear the content of that PCR. Sometimes even to use it and extend information in the PCR. TPMs start in locality 4, and in that level, the TPM expects a command from the platform. At boot up, the platform initializes the TPM, probably performs TPM2 startup, and the locality level changes to the next one. Then we are handed off to the UEFI or BIOS. We get another change in locality level. And then we are passed to the bootloader and the operating system.
Usually, the operating system and our applications would work in locality 0. If you're working on an IoT system, however, you might be working in a different locality level, a higher one with more capabilities. It really depends where lives the solution, the software that you're developing. You could be a UFI vendor, for example, then you would most likely use locality level 3. Here is a better overview of the different levels and how they are linked to the different stages of the system boot. And also, what is the expected software type to use these locality levels. On the bottom of the screen, you can see the so-called extended localities that were added later. Some are reserved, but most are actually available, and depending on the needs, the technical committee of the TCG can decide to reserve additional ones for your use case. In most applications, however, the existing 24 PCRs with the typical 5 levels of locality are sufficient. At system start, the TPM is in locality 4, and the CPU will instruct the TPM to perform a TPM2 startup. Of course, it is the UFI BIOS code that will send the instructions, but the host is the CPU that sends the commands to the TPM. In turn, the TPM will reset all 24 PCRs from number 0 to 23, along with other initialization steps. And then the UFI or BIOS will extend information into the first PCRs, usually PCR from 0 to 7, with important information about the state and integrity of the UFI configuration and so on. On the bottom of this slide, I've added a link to the Linux TPM PCR registry for more information about the real-world usage of PCRs in personal computers. Now, let's get back to our example. The operating system works in locality 0 and therefore could not reset PCRs from 0 to 7. The locality level does not allow such commands to succeed, including the OS would not be allowed to perform PCR extent on the PCRs from 0 to 7 because the OS is in locality 0. This means that the information provided to us from the system start by the UFI or BIOS into these PCRs is protected until the next reboot. And we can use that in our operating system or during the boot stages. This information can be of great value. This, of course, falls on the assumption that our UFI is also genuine and it has successfully passed a secure boot process. Or better yet, a measured boot process. And one last note about locality levels. They can be used in TPM 2.0 policy crafting. We'll talk more about TPM policy in the next lecture. Here is an overview of how locality levels relate to PCRs. Usually at OS runtime, either in user space or in the operating system in kernel space, PCRs from 8 to 15 are used, because in locality 0 there is no PCR reset allowed for these PCRs from 8 to 15. We can extend new data, new hash digest, new information, and it is protected until the system reboots. Very important to note also that any locality can reset the debug PCR, PCR16, and PCR23, the so-called application PCR. This is what we'll use for our labs. Going further, here are some real-world examples how PCRs are used. Microsoft's solution to disk encryption and protection of the operating system uses PCRs from 8 to 11 or 11 to 14, depending on the version. The Linux popular bootloader group uses PCRs 8 to hash the kernel command line, and this way it can verify the kernel launch command. Then it further extends the kernel image that is going to load in PCR 9. This means that once the Linux kernel has booted, it can verify the state of the system and see if it's genuine and should continue forward. This also gives us control at bootloader level in group to decide, is the PCR9 digest matching what I'm expecting to boot and not boot at all? Later, the kernel can verify the kernel command and decide, okay, this is not the command I expected,
And this might be because they're trying to boot from a different root FS, and this way we can prevent an attack on the system. This all adds up when we start using the TPM 2.0 to generate signed proofs as evidence of the state of the system.